two possible ways to start with your empirical formula. You'll either directly be given grams of each of the individual atoms that go into your formula, in which case convert it into moles, and you can move into step 2, or you'll be given the percent composition. Okay, well, if you've got a percent, that's out of 100. So just assume you've got a 100-gram sample, figure out what the mass would be for each element in that 100-gram sample, then convert to moles. Okay? Once you've got your mole amounts, you'll divide these all of the mole amounts by the smallest mole, round or multiply as necessary to get to your whole numbers. This will then set you up with your empirical formula. Once you've got the empirical formula, if you're asked to do the molecular, you'll need to determine the molar mass of your empirical formula, and then you'll divide the correct molecular molar mass, which will be something given to you, by your empirical molar mass, and that'll give you a whole number. Once you've got that whole number, you multiply the whole numbers in your empirical formula by whatever that number is. I know that says 2, and I forgot to fix that, so it doesn't say 2. Multiply the numbers by, oh, I know why it says 2. From step 2. Okay? Hence it says from and not by. Okay? So, because a request was made to do another question, I really quickly put together this one, so hopefully the numbers work. We'll see what happens. Okay, an unknown sample was found to be 39.9% carbon, 53.6% oxygen, and 6.5%, just 6.5%, you know, why not? Hydrogen. Literally just made this up 2 minutes ago. What is the compound's empirical formula? It's a good thing I know my grammar. There's apostrophe in there. Compound's empirical formula. Spend a quick second, probably a couple minutes, and put it together, see if you can't figure out what the empirical formula is. So we're here. Convert your percent composition. Assume a 100-gram sample. If you have a 100-gram sample, how much of it is carbon? 39.9 grams. Why 100 grams? Because it's a percent. It's the whole reason. We can then cancel out our percent and we end up with 39.9 grams. So 39.9 grams of it are carbon. What would the mass of oxygen be in that 100-gram sample? 53.6. Okay. What would our mass of hydrogen? 6.5. All you have now done is, as far as the ladder goes, is move backwards. You've moved from your percent composition to now grams. Well, the whole point of an empirical formula, CXHYOZ, is to figure out what X, Y, and Z are. Well, what units show up on those numbers? If I give you the formula NaCl, what does that mean? There is one sodium in sodium chloride. It is a number of atoms. Okay? Remember, we're looking at an incredibly tiny scale, so counting the number of atoms would be a massive number, particularly in a 100-gram sample. So what can we do instead of looking at the number of atoms? Move up to moles, which is now just a really large number of atoms, and we can work with numbers that aren't powers of 10. So our very first step is to convert everything into moles. Why? Our empirical formula tells us units of moles. So if I can get all of my elements into units of moles, all I got to do is shovel those numbers into my empirical formula, and I have the potential for an empirical formula. The issue, though, is that our empirical formula, by definition, is the smallest whole number ratio. When you go through to do that division, or do your calculation, very rarely are you going to end up with the smallest whole number ratio for moles. So what you'll have to do is one extra step. You'll divide every single mole amount by the smallest mole value. This will immediately take you down to what is quite likely your smallest whole number ratio. Okay? So, when we go back to this sample, we said how much of it was carbon? 39.9 grams was carbon. How much was oxygen? And how do I convert each of these into moles? I use the periodic table. Interesting. The first step in this case was to do what? Convert to moles. Hey, that sounds familiar. Did maybe some weird hairy person tell you that the first step you should do would be convert to moles, always? Look at that. Hey, it works. How do we do that conversion? Pull our numbers off the periodic table and we get 1 mole is 12.01 grams. Or if you're me, you realize the 0.01 probably isn't going to matter, so you just kind of ignore it. Okay. Oxygen. Hydrogen. 1, particularly because I did the calculation, and that's what I assumed. So that should make it easier. We go through, punch it into our calculator, and we get for our carbon 3 point what? I'm going to say that's wrong. Moles of carbon. Now you're right. Next one. It's 3 point. Way to head me off the path. And the last one. Moles of hydrogen. So what we could now do is take this information and dump it into an empirical formula, and into a formula, and we'd end up with C3.325. And I'm waiting for someone to ask me this question. H6.5, O 3.35. How many of you would be happy with formulas with all these decimals in it? Right. Most people aren't happy with it. It looks awful. Okay? So we said this is nonsense. We're not using formula, or not making our formulas with a bunch of weird decimal values in it. It makes no sense. So we go through and we simplify this formula by doing what? We divide all 3 values by our smallest number, which happens to be 3.325. So that that formula was nonsense, and we end up with 1 point something. What was it? Okay, you're all equally lazy as me. That's fine. 1.9? No, 1.00 sounds a little more right. Okay, the next one, yeah, 1.9. I believe that. Okay, sorry, that's my fault. So we can now put this into our empirical formula, and we end up with the formula C1, H 1.9. Ooh, 1.9. That's that weird decimal. Round it to 2. O 1. We'll round to 1. Did our numbers come out perfect? No, but they are within a really close approximation of that whole number. Okay? When you are working problems in lecture, you will come out very, very close to a whole number, or very, very close to a half number. Okay? The half number, if you encounter that, then you can talk to me. If you don't encounter it, don't worry about it, because I don't want to make this worse or spend more time than we have to on this. Okay?
Are we required to write out the ones in the empirical formula?
If we were going to write our empirical formula, should we actually include the ones? No, and technically it's wrong to show the ones. This is one of those stupid rules. You aren't supposed to show extra information. So we'd be writing CH2O.
It has to be written in that order, too.
We're waiting for that question. You notice when I listed out in the problem, I said carbon, oxygen, and then I did hydrogen. When we write out the formula, I wrote carbon, hydrogen, then oxygen. Why this change on the hydrogen and the oxygen? Yeah, I'm not surprised you aren't aware of this. There is a rule when it comes to putting together a formula for covalent compounds. The sequence of atoms in your formula, someone said this is the sequence it must be. If the atom doesn't show up, you don't worry about it. The proper sequence, carbon, hydrogen, oxygen. Okay. You don't know that. I think it's called the Hall rules. So if you look up Hall rules, you might find it. Not a big deal. Don't stress on it. The only reason why I screwed it up in the problem is I wrote it too fast. Otherwise, I would have written carbon, hydrogen, then oxygen, so we didn't have that question pop up. So don't stress on the order. You will not be asked questions on the order. Okay. Questions? So what is our answer for this? CH2O. So you guys all have awesome, actually can I erase everything? You all have awesome skills at, what is that awesome skill at? Lewis structures. So you could now draw a Lewis structure for CH2O, and I'm going to jump to the conclusion that you should be able to come up with this compound, or with that Lewis structure, CH2O. Cool, we got a Lewis structure for this. Unfortunately, it turns out that this compound does not react the way that compound reacts. Why? Because empirical formulas are largely nonsense. Okay, what you need to actually be looking at is the molecular formula. Well, how do we move to the molecular formula? We have to have more information about our compound. That more information is the molar mass of our compound. Okay. So after doing all of that empirical work, we now find out that the molar mass of our compound is 60 grams per mole. So it's the same sample. We know the empirical formula was CH2O. And we now know that whatever our actual compound is, has a molar mass of 60 grams per mole. What is the compound's actual molecular formula? And if you've been paying attention to the slides where I actually told you how to go through and solve this, you should be able to solve that. We'll give you the next couple minutes to see what you can do with this if you got questions. So if we go ahead and start up again, we need to figure out as our first step is the empirical molar mass. We figure that out by going to the periodic table. Carbon has a mass of 12. Hydrogen has a mass of 1, but there's 2 of them. Oxygen has a mass of 16. We add those up and we get a magic number of 30 grams per mole from your empirical formula. The next step is we take the actual molar mass, which was 60. We divide it by our empirical molar mass, and we end up with 30, and we get 2. What this is saying is that our actual compound has twice the mass of our empirical formula. So what do we have to change in our compound, or our molecular formula, or our empirical formula, to get to our molecular formula? I have to multiply everything in that formula by 2. How many carbons are there? There's 1 here, so I would multiply by 2, and I'd end up with, C2. H O2. Okay. We now have the molecular formula. Okay. As I started to allude to, well, actually, before we do that, was there a question there? Or just like, why did I do that? What do you mean, what the heck? I don't know what to do with that. Okay. Have you seen this formula before? Vaguely familiar. It's a good half answer. I like it. Let me rearrange this a little bit for you. if we look at the compound now, we have a drastically different reactivity from our initial Lewis structure. Our initial Lewis structure was technically not something known as an aldehyde. This is known as a carboxylic acid. How do you think carboxylic acids act? Like acids. That's why we call them carboxylic acids. Believe it or not, take advantage of the name. It can help you out. Okay? So that gives us something that we can use about its reactivity, which is what we're pretty much going to be moving to in the next section. So questions on empirical formulas, molecular formulas?
Where did we get that 60 grams?
Was found to have a molecular mass of 60 grams per mole. I know, sometimes I give you information outright, sometimes I don't. So it's understandable. Make sure you read your questions carefully. That's how you would get it. It's not something that you would be able to calculate. You'd have to be told it.
And one other thing, what made you move that H from H4 out into... Did you just answer that? Or?
No. It's knowledge, yeah.
Okay.
I knew what compound I was aiming for a molecular formula, and I backtracked from that to get this question. And I tried to pick something that you guys already knew. I knew you'd seen acetic acid. Why write the formula differently? You're trying to represent some different information about the chemistry. The formula HC2H3O2 gives us information. This is now acetate with a hydrogen, so we have acetic acid. C2H4O2, there's a couple ways you could put that compound together. It removes information about its reactivity. So depending on what you're looking at, you may want to know something about its reactivity. You write it out as the top formula. If you don't care or you don't know, you write it out in the bottom. You just total of what all of the elements are. Okay? Which is pretty much Gen Chem. Gen Chem's happy little home is in that bottom section. Okay? So, how many of you love dealing with numbers, calculations? Nobody? Okay, I agree with you. I don't like dealing with them either. This whole next section then is going to be pretty much mind-blowing, or most of it, as far as forces and implications go. There are no numbers. Right? However, you still have to think and work through and come up with explanations to different things. Okay? So, and thermodynamics is too much numbers. You don't have to worry about that. Okay? So, in our simple overview, what makes an atom? Protons, neutrons, and electrons. All right? What makes a compound? Two atoms. Okay? So if I said Beverly in the corner over there was an atom, and I'm an atom, would we be making a compound at this point? No. Why not? So it's not just two atoms. Okay? What makes a molecule? Yes, two atoms is part of it, but what else makes a molecule? Two atoms together, but why are they together? They have to somehow be interacting through sharing of electrons between those individual atoms. So there is an exchange between those two that allows for it to become a compound. Okay? So what we end up looking at is how those two atoms interact. If there is no interaction, there's no compound. If there's a weak interaction, we can now say we have some kind of force involved in it. As that interaction gets stronger and stronger, we stop calling it a force and we start to reference it as a bond. And we can move to an ionic bond, where they're transferring electrons from one atom to another. If they now move to sharing electrons equally, we now have, not a drum roll, but okay, a covalent bond. Okay? So we end up moving from forces up to bonds. And everybody goes, oh, well, that's mind-blowing. It's way too hard to understand, to think about, or believe. Really? Okay? What do we have here? Two smiley faces. These smiley faces represent people. Would we expect these people to have any interaction with each other? Oh. kind of separated, they're both smiling, but have they proven any interaction between each other? No. No. What happens if we do that? Is there an interaction now, potentially? Yes, you're being too literal here. They've now gotten closer, and they're clearly making weird googly eye faces at each other. Okay? So we're starting to see some kind of interaction. Okay? What happens now? Now they're looking at each other. Okay? We've now increased the interaction. Maybe now, instead of them just staring at each other and passing notes in the hallways or pulling on each other's hair, what do we find? They're now dating. What happens after dating? You break up and start again. Eventually, what happens? You stick with one another and you get married. Okay? When we look at our individual relationships, we've already done and categorized the exact same thing that we are categorizing with molecules. We have two atoms that don't interact with each other. Now they start to see each other, and there's this now weak attractive force between them. Somehow they're getting closer to each other. Eventually, maybe everything aligns perfectly where they now start dating. Okay? If they date well enough, it sounded kind of weird, but if they date well enough, they can now get married and they're now permanently connected and have potentially equal sharing of stuff. Right? At least the way the law looks at it. But are all marriages exactly the same? No. Are all bonds exactly the same? Are all dating couples exactly the same? No. So what we've done is generate kind of this overview idea of what's happening within it, but then we can subcategorize different relationships. The same thing is happening with molecules. When we take two atoms and we bring them near each other, what happens? What do we expect to see? That is what we're looking at when we look at bonds. That is what we're looking at when we look at forces. All we're trying to do is classify those arrangements and come up with some way to then predict success. Okay? And we have attempted to do that with marriage too. Go through and say, only these marriages work and these ones won't work, so we won't allow those. Okay? We're doing the same thing with chemistry. And when it comes to those relationships, sometimes it works great. Sometimes our predictive powers don't work so great. Okay? But that's what we're trying to do when we're looking at our forces and ultimately our relationships. Okay? So we can now look at that marriage end of it. We've talked about these. This is now the intramolecular. We're saying, whoop, two things have now formed a strong attraction between each other, and they are now bonded. Okay, we're in that marriage section. Within that marriage section, can we subcategorize our types of bonds? So when we're saying intramolecular, we are now saying they've already formed a bond. What are the types of bonds present? We've done this before. We had three types of bonds present. We had ionic, we had polar covalent, and we had what I like to reference as just covalent because I'm lazy, but technically non-polar covalent. So this is good review. We came up with some rules that allowed us to quickly say that bond is ionic, that bond is non-polar covalent. What were those rules? I don't like that color, so I'm going to fix that while you guys think about it. You got rules for identifying any one of those bonds. What's that? Metal and non-metal. Metal and a non-metal makes an ionic bond. Okay. That is really just our rule of thumb. Okay? It's not an exact science, but it gets us pretty darn close. So if we see a metal and a non-metal, I got an ionic bond. Okay? Our official rule is that the difference in electronegativity, I'm only going to write this out once because it's a lot of letters. Oh my gosh. Difference in electronegativity. Delta for our difference, electronegativity, carries the symbol, I believe, chi is what that's supposed to be. Okay. If our difference in electronegativity between the atoms is greater than 1.7. Okay. Yeah, that may seem like an arbitrary number. That's because it really is. Depending on the textbook, depending on the instructor, you get a slightly different number for that. Okay. Pull up a table of electronegativities and start picking metals and nonmetals. What you will find is the difference in electronegativity for almost every metal and nonmetal bond is greater than 1.7. That's why our rule of thumb works really, really well. Okay? Between the other two, do we have another definition? Okay, this one gets trickier. A polar covalent bond is a non-metal bond. But guess what a non-polar covalent bond is? Non-metal. So that, while true, doesn't really help us out. We want something to allow us to distinguish those. Unequal sharing of electrons for a polar covalent. How do we measure our ability to share electrons? The difference in electronegativity. How many of you memorize electronegativities? I call BS. Okay. So while it is true, again, a polar covalent bond is an unequal sharing of electrons, that's not really going to help us out. Okay, so along those lines, our unequal sharing of electrons gives us a difference in electronegativity that is less than 1.7, but greater than 0.5. So I just gave you a big hint on what our non-polar covalent bond is. A difference in electronegativity less than 0.5. Okay, but again, you haven't memorized electronegativity, so those definitions aren't helping us. You've got good things, but you'll never use those. Okay, yeah. A non-polar covalent bond, one of the extra rules that was useful to memorize was that carbon bound to hydrogen is a non-polar covalent bond. Okay. It is defined as one. That, I would say, is an extra memorization thing, though. There's actually another step on this that doesn't require as much memorization. Anything bound to itself. Why? They will have the exact same electronegativity. So if I bond fluorine to fluorine, fluorine is the most electronegative element. So I bond fluorine to anything, it should be a polar molecule or a polar bond. But if I bond it to another fluorine, the electronegativities cancel, and I get a non-polar covalent bond. So when we're looking for our rules, our non-polar covalent bond, carbon to hydrogen, and then anything bound to itself, sets us up with a non-polar covalent bond. Yes?
These would cancel, like they're both negative, so how?
They are not both negative. They are both electronegative. Okay. Negative says fluoride. It's not fluoride if we look at the bond between F and F.
Yeah,
Okay. So what we'd be looking at is how each of them pulls on the electrons. Well, if their electronegativities, as a measure of their ability to pull on the electrons, are identical, they are both equally pulling on the electrons in that bond. Well, there's two electrons in that bond. One goes to this fluorine, the other one goes to this fluorine. What charge would build on each of those fluorines? 0.
Is that why diatomic? Does that relate to diatomic? No.
No, it doesn't relate to diatomic. But all diatomic molecules will be nonpolar.
Yeah.
Okay? Other questions? So we've got two workable definitions. Ionic compounds are metals and nonmetals. Nonpolar covalent compounds are carbon to hydrogen and anything bound to itself. Okay? How do you know what a metal is? The little hand gesture was not a bad one. Does that show a positive charge? No. So sort of positively charged works, but that doesn't show a positive charge. So I need something else. What about the periodic table? This is where your hand gesture was okay.
The left side.
The left side, and in particular, left of that staircase, the bolded staircase. Remember all of those were metals? Everything to the right of that staircase? Non-metals. And then we're in just a mess of things on the staircase because that's some of those are metalloid, some of them aren't. Okay? So thankfully I don't ever ask you those questions. Okay? So if you know where your metals are, you can identify ionic compounds immediately. Trigger, that's an ionic compound. You trigger and you go, I don't think that's an ionic compound because there's no metal. Then you're now stuck between polar covalent and non-polar covalent. So now you actually have to look at both atoms of the bond. And what you will decide is, are both atoms or one of the atoms a carbon and one of the atoms a hydrogen? Non-polar covalent. Are the atoms the same thing? Non-polar covalent. Okay? What happens if you look at the atoms of that bond and they are not ionic and they are not non-polar covalent? What's that? Then it's going to have to be polar covalent. Everybody seems to like the everything else definition, so I was surprised that didn't already just come out. Okay? Is that technically true? What type of bond do we have between lithium and lithium? I heard nonpolar covalent or covalent. I'd accept both of those answers because that is anything bound to itself except nonpolar covalent needs to be nonmetal to nonmetal. Lithium bound to lithium is metal and metal. Okay. What is that bond? Not on this classification. I don't care. Technically, it's a metallic bond. Okay. We don't need to worry about those for this class. Okay. So what we've now gone through and done is classified any bond. So I can take any two atoms, put them near each other, and you can tell me what bond is present. Okay. Well, is that particularly useful? Does that tell me anything about the phase of the compound? No. Okay. Does that tell me anything about how it's going to react? No. So yes, identifying the bond is helpful because I now have some information about it, but that doesn't give me any reactivity or anything to do with what it will do with the rest of the environment. To figure that out, I have to push a little bit further. And I now have to see how individual molecules will interact with other molecules. Okay. It's a trickier question to go through and do. So let's go through and do it. We got a whole smattering of possible options up here. So we'll look at them kind of randomly as we go through this. Let's start with what I would argue to be the easiest one. We're looking at our test sample molecule, or test sample bond, sodium chloride. What type of bond is there? We have an ionic bond. What I am now concerned about is how does that ionic bond interact with another molecule? The other molecule I picked happened to be the same kind, sodium chloride. Okay. So what I'm now asking is which of these interactions is more favorable? So number one, you'll notice I did not show a solid line. Why not? What does a solid line represent? A bond. These are not bonds. These are now interactions. How does this sodium chloride interact with another sodium chloride molecule? Okay. Which of those interactions is better? Okay. Same is a possible option. Better is a possible option. Better doesn't quite work. We'd have to say top is better, bottom is better, or same. 3 options. 30% chance. So far I've heard 2. Top is better, same. Anyone want to say bottom is better?
Bottom is better.
Okay, way to throw it out there. What information do we know before we go out and look at the interaction between these two molecules? What information do we know about the bond first? What can you tell me about an ionic bond? What's that? In ionic bonds, they transfer electrons from one atom to the other. One of them is going to be negative, one of them will be positive. Which one will be negative? I don't accept chlorine as an answer. Or chloride, but fair choice. And I won't accept nonmetal, though technically still true. The anion would be negative by definition. Still don't accept it. Still don't accept it.
The one on the right.
So when we move to the bottom one, the one on the right, sodium is going to be negative. How do we determine which atom should take the electrons? Electronegativity. The more electronegative atom is the one that takes the electrons. Which atom was more electronegative? Chloride or chlorine. I'll accept both on that. Which means our chloride is negative and our sodium is positive. So we are adding information to our drawing. Let's move to the next one, the top one. Which atom is more electronegative now? Same thing. And the bottom one? Same thing. Okay. Does this give you extra information about which of these interactions is more favorable? Which interaction is more favorable now, the top or the bottom? Ooh, we still got a mix here. All things in nature, chemistry, life, strive for neutrality. That is the lowest energy possible. Remember, charge is incredibly bad. Don't stick your finger in the electrical outlet. Okay? Full of charge. I need to neutralize charge as much as possible. So if I'm now bringing those atoms near each other, if I bring the chloride near another chloride, what happens to the charge? It goes up, and ultimately we would say it repels. Why do they repel? They're the same charge. That moves to a higher energy state, not a lower energy state. We aren't neutralizing the charge. So when I bring chloride near chloride, that is a bad interaction. I want to neutralize or avoid that interaction as much as possible, which means what happens with that bottom interaction? It is a horrible choice. What about the top interaction? What happens when I bring the negative near that positive? They cancel. Okay, they attract each other. They neutralize that charge, which means that top interaction is better. I'm going to go with awesome. Better was probably a better choice because it had less letters. Okay. That is our better interaction. Okay, well,
I was thinking of stacking. That's
what happens if we now move to our bottom case? Same idea. Which interaction is better, top or bottom? What do you mean it doesn't matter?
Both all negative. They're all negative.
No,
No?
they are not all negative. What type of bond do we have? We have a nonmetal-nonmetal, which is a nonpolar, in this case, covalent bond. What charge builds on the hydrogen? No charge. What charge builds on the carbon? No charge. If we apply this information out to our other molecules, which interaction gives me less charge? It doesn't matter. Both options are equally valid in this situation. Okay. What does that mean for us? Well, if I take a compound, say sodium chloride, and I now put it around a bunch of other sodium chlorides, I would end up with a compound known as, come on now, sodium chloride. What phase is sodium chloride? If I go through and I take this carbon-hydrogen interaction, and I now make sure I've got a whole bunch of these, what I'm going to end up with as a compound will be methane. What phase is methane?
Yes.
Interesting. I have a difference in phases here. So one of the natural tendencies for students to go through and do is to say, well, sodium chloride has an ionic bond. And since it's a solid, that must mean the ionic bond is very, very strong. And if I look at methane, methane has nonpolar covalent bonds, and it's a gas, which must mean the nonpolar covalent bond is incredibly weak. Technically, that's wrong. The covalent bond, the nonpolar covalent bond, is stronger than an ionic bond. If it is a stronger bond, why am I in the gas phase? The only thing keeping me from being in the gas phase is stronger attraction between molecules. If methane has a stronger attraction than sodium chloride, or a stronger bond than sodium chloride, why does it go up into the gas phase? It's not the bond that determines the phase. It is the attraction between the molecules, which we will now change from being a bond, and we will call it
Strong force, weak force.
a force. Okay? Yes, that's physics. In sodium chloride, I have a stronger force than in methane. Okay? And that's because in sodium chloride, I want to cancel those charges. Okay? So when I bring multiple molecules near each other, I'm trying to cancel out that charge, so I organize the molecule to keep those charges aligned. That is now a really strong attraction because I am decreasing the charge. If I go through and look at the, whatever that one is, what is it? CH. Is there any reason for those molecules to interact? No, which means that force is now very, very weak. It is so weak that when we first look at that, we would say, what kind of force is there? How much force is there? None. That's our initial pass. We looked at these, we said ionic compounds generate these wicked strong forces. So I'm going to come up with a name to represent those forces. The nonpolar covalent compounds generate incredibly weak forces. They are so weak, I don't even care about them. They are irrelevant to the overall understanding of our molecules and understanding of chemistry. So let's go through and try and name these. The top one. It's a strong, attractive force. I want to pick a name that allows me to say where that force came from. What kind of name do we want to use here? What kind of bonds generated it? An ionic bond. Okay. So being the super creative people that we are, okay, thank you chemists for this one, we call this force, technically we call it ionic bonding. Does anybody have a problem with referring to it as ionic bonding? Yeah. We're not referencing a bond, we're referencing the attractive force between ionic compounds. That's not a bond, it's a force. Okay. Yes, it is confusing. So another term that is starting to make its rounds and hopefully will overtake ionic bonding as a name is referenced as electrostatic. It is an electrostatic force. Okay. Also referred to as ionic bonding. It is confusing because ionic bonding is not a bond in this case. Okay. It is the force. When we move to this weak force, we said that force was so incredibly weak that it is zero. Okay. How often do we name things that have nothing? Except for zero and nothing, really nothing. Okay? We never associate a name with something that doesn't contribute anything. Okay? Turns out it does contribute something. Okay? And because it does contribute something, the person that discovered that it does contribute something named it after themselves. That person's name happened to be, I may have actually just heard it out there. Van der Waals. So the name you will sometimes refer to that force as is the van der Waals attraction, or the van der Waals force. Okay. For some reason, this particular interaction has picked up enough popularity that people have started to say it's dumb to name things after people. Let's actually name them from what is happening or referenced in them. And the name that is starting to become more and more important is a dispersion force. Okay. And it's a dispersion force because when we look at an individual molecule, we have an electron cloud. Electrons are bouncing around within that. At any given instant, those electrons can be all on the left side of the structure or all on the right side of the structure. On average, the electrons are equally everywhere, which means on average there is no charge within the molecule. Okay. Just like on average for this class, we're at a 75%. That means everybody in here should get a C, right? Because that's average. No, there's some people that did better than that, some people that did worse, right? So we should spread the grades. What's happening with electrons? They're also spreading. And in some opportunities, the electrons are all on one side of the molecule. If I put all of the electrons on that far right side of the molecule, what is left exposed over here? A hydrogen. Well, what makes a hydrogen? One proton. So what is exposed on the far left of the molecule? A proton. With what charge? A positive. The electrons, we said, were shifted all to the far right. What charge were the electrons? Negative. So what ends up being generated in this molecule at random instants? A partial charge. That partial charge makes a stronger force. It is a temporary dipole, a temporary charge, due to the dispersion of electrons, hence dispersion force. Okay. The last part of this, I have no idea why this name actually comes into it. London dispersion forces. You will hear me refer to them as London dispersion forces throughout the rest of the semester, and because London dispersion has way too many letters, LDF. Okay. We've just identified two forces, the absolute strongest force and the absolute weakest force. Are there other forces? Yes. Okay. Everybody okay with what's written up there? Because I'm about to erase it all. Okay. Which interaction is better? In the upper right-hand corner. Why the top one?
Because oxygen is more electronegative, so it has...
Oxygen is more electronegative, so it carries that partial negative charge. The hydrogen carries a partial positive. We add that information all the way through. The top interaction cancels more charge than the bottom interaction. How about that bottom case? Top or bottom? Oxygen being more electronegative will carry the partial negative. Our carbon being partially positive will carry that, or less electronegative will carry the positive. And we end up with the top interaction being our preferred force again. This interaction, stronger or weaker than the previous interactions we've talked about? Either one of these. Sorry, I just heard your question. We talked about an ionic force, and we talked about our London dispersion forces, our LDF forces. Ionic was stronger than LDF, but these two forces, or these two interactions, would we expect these to be stronger than ionic? or weaker than ionic? Why should they be weaker than the ionic? Yeah, smart people. Partial charges are generated here. In an ionic bond, we had formal charges. Formal charge means there's a big enough shift in electrons to generate a permanent charge. A partial charge means I'm not there yet. I'm less charged. If it's less charged, I'm going to have a closer interaction to the LDF style. So both of these should generate a force that is weaker than ionic. Should it be stronger than LDF? Why? There is a partial charge in these compounds. So we would expect that new force to be somewhere in between these as far as our strength. Let's come up with a name to reference where these came from. Okay. We could reference these as being polar covalent bonds because they are polar covalent. That's why. How do we know they're polar covalent? Oxygen, hydrogen, oxygen, carbon. It's helpful. Is it a metal and a nonmetal? No, so it's not ionic. The other one was nonpolar covalent. For it to be a nonpolar covalent bond, what had to be the case? Carbon to hydrogen or?
Anything bound to itself.
Anything bound to itself. Does the nonpolar covalent bond classify? Nope. Which means polar covalent. It's our only choice left. So this new force, just like we did for the ionic one, which I should be writing as electrostatic, we could name according to where it came from. And we could call it a polar covalent bond. What's the problem with calling it a polar covalent bond? It's not a polar covalent bond. So at least at this point, chemists got it right and said that that was a dumb idea. We need to come up with a name that still represents where it came from, but doesn't name it the exact same thing as something that's entirely different. Not quite yet. We've got partial charges built into this, which means we have two poles, one positive, one negative. So if I look at an individual molecule with a negative and a positive, it has two poles. What could I name something that sounds kind of fancy, like it has two poles? We could call it two-pole. I might get a little confused. What's that? Dipole. Di for two. So that first molecule, instead of calling it polar covalent, I can call it dipole, because that's what it is. It's got two poles. What does the other molecule have? Two poles, so let's call it dipole. What is the attraction between two molecules that are dipoles? I know you're all like, wow, that must be really hard to come up with. I don't know how they figure this one out. What is the name given to this force? Dipole-dipole. That's it. Okay? Referencing where the force came from. It is the attraction between a dipole and a second dipole. Okay? Both of these forces are classified as dipole-dipole. Are both of those interactions predicted to be the same strength? Why? Why no? It has to do with our difference in electronegativity. When we looked at comparing our ionic bonds, those had very large charges, positive and negative. Okay? That made it a very large or strong force. Okay? If we go through and look at the charges generated between oxygen and hydrogen, those charges are larger than the charges generated between oxygen and carbon. Why? And I will accept the smart aleck answer in this one. That's actually the correct answer. The difference in electronegativity between oxygen and hydrogen is larger than the difference between oxygen and carbon. That larger difference means a larger charge that is built. The larger the charge, the more it looks like an ionic bond, so it becomes a stronger force. Hydrogen is the least electronegative element that is a non-metal. So if I bond hydrogen to oxygen, the second most electronegative element, I'm going to generate a massive dipole. It is so big, it is starting to approach an ionic bond or an electrostatic force. But it's not there yet. Okay? It is also so big that it doesn't make sense to refer to it as a dipole-dipole or even a London dispersion force, because it is that close to it being an ionic bond. So I want to give it a new name that references how I made that compound. We took the least electronegative element that's a nonmetal, hydrogen, as a hint, hydrogen, and one of our most electronegative elements, oxygen. What type of force should I refer to that as? Hydrogen, and this is where chemists screwed up pretty thoroughly. Hydrogen, it hurts to say it, bonding. It is not a bond. Hydrogen bonding is the attractive force between two molecules where one of those, or where those molecules have a hydrogen bound to an electronegative element. So hydrogen bonding as a force is generated from a legitimate hydrogen bond and another molecule. Okay? Yes, you may not like that. Tough, that's the way it works. There's currently no other name. We could make one up, but that doesn't mean it's going to change on your test. Hydrogen bonding is an example of dipole-dipole. So why not write hydrogen bonding under dipole-dipole? It's a stronger force, so we're trying to represent that hydrogen bonding is stronger than dipole-dipole. How do I know I have a hydrogen bonding force? What things did I need to have? Number one, I need to have hydrogen. What else did I need to have? Oxygen is a very important aspect to it. We're trying to generate the largest difference in electronegativity possible. So oxygen is a classic example for hydrogen bonding. What else is necessary? Has to be an electronegative element. Is oxygen the most electronegative? No. What happens if I bond hydrogen to fluorine? It's going to be an even stronger attraction, which means fluorine is also on my list. And it turns out one more element gets added to our list. Let's all have some fun. Hydrogen's all about fun, right? Fun. Waiting until most of the class laughs. Yeah, I agree. I think it is pretty awful. It wasn't my idea. Okay. Hydrogen must be bound to fluorine, oxygen, or nitrogen to have a hydrogen bonding interaction. Does that mean just because you have hydrogen bound to one of those elements that it is hydrogen bonding? Of course not. Good answer. Do I have a hydrogen bonding interaction? No, this is not a hydrogen bonding interaction. This is a hydrogen bound to oxygen. For there to be a hydrogen bonding interaction, what do I need? A second molecule. Second molecule, do I have a hydrogen bonding interaction? No. I still have the hydrogen bound to fluorine, oxygen, or nitrogen, so that is still present. But hydrogen bonding is what type of force? A dipole-dipole. Is the OH bond a dipole? Yes. Is the CH bond a dipole? No. Do I have a dipole-dipole force? No. If I do not have a dipole-dipole force, I cannot have hydrogen bonding. Okay? Tricky? Yes, absolutely. But that's the way it works. Okay. So we've got 4 primary categories when it comes to our forces. Our ionic or electrostatic, hydrogen bonding, dipole-dipole, and London dispersion and or van der Waals forces. Okay. Just like we did with our bonding, we want to be able to quickly look at a molecule and start to classify these interactions. How can you possibly figure out that you have an ionic or an electrostatic force possible from a molecule? When did you get an ionic or an electrostatic force? When the bond was ionic. How do we get the London dispersion force? When the bond was nonpolar covalent. How do we know we had a dipole-dipole force? When our bond was polar covalent. So remember those rules of thumb on classifying what kind of bond structure we had? Why are those important? That tells us our force. Okay. Hydrogen bonding, how do we know we have hydrogen bonding? First we have to have a dipole-dipole, then we have to have a hydrogen bound to nitrogen, oxygen, or fluorine. Or NOF. I prefer NOF. Because I'm not a funny person. You thought the first one was bad. Our summary of interactions. Okay. I'll go back in a second because we're technically done. Okay. Why is this important? Phase transitions, vapor pressure, viscosity, surface tension, solubility, reactivity. All of those come from looking at first classifying your bond, then classifying the force. Okay? That is where we will pick up on Tuesday, is coming up with how we can manipulate understanding those forces to predict each and every single one of those possible interactions. That is why being able to do this is incredibly useful. Please, and I'm serious, please pack up. The last thing I want to kind of talk through is just going on with this, what's happening with this color wheel. If I have a London dispersion force, where did that come from? A covalent bond. The London dispersion forces are colored black. Covalent bonds, black. If I have a dipole-dipole force, I came from a polar covalent bond. The colors match across. Why am I showing it even on a color wheel? Why bother? Okay. What you are looking at, starting at a London dispersion force, is a force so weak that there's barely any interaction whatsoever. As we increase the attractive force between those individual atoms, what happens? We move up to a new classification, the dipole-dipole force. As we continue to increase the attraction between those molecules, we have a hydrogen bonding force. As you continue to increase the attraction between the atoms, you can move to an ionic force. As you continue to increase the attraction between those two molecules, you move from being a force to an ionic bond. As you continue to increase the attraction between those two atoms, you can move down into a polar covalent bond, and then all the way down into a covalent bond. When we are looking at these attractive forces, it is a spectrum. Okay? It is a continuous relationship, not discrete. Okay? We'll talk about that discrete aspect again on Tuesday because it is an important distinction to make, but then we'll look at some properties of using this.